Dr. Bbosa science, kwano kwa beti science, love ya Bbosa science, truth na beta, truth na omega, truth na alpha science.
The Science Foundation College enamave ku Lwejjinja ng'oyingira kilomita emu. Ssomero lya Dene Boarding eri abawala n'abalenzi. Ku O-level tusomesa arts ne sciences ate A-level tusomesa sciences zokka. Omwana mulete ku The Science Foundation College. Ffe tusinga okusomesa sciences. Okumanya ebisingawo kuba ku 0753 8 27 09. The Science Foundation College, based on sciences and based for sciences.
Dr. Bbosa is a teacher at the Science Foundation College, the best school that teaches sciences. At A level, we teach sciences only. At O level, we teach arts and sciences. Today, we are going to study the periodic table. This is a tabular arrangement such that columns contain elements with electronically similar atoms. The rows of the periodic table are called periods. The columns of periodic table are called groups. There are 7 periods and 80 groups. Some special groups. Group 1A. This consists elements hydrogen, lithium, sodium, potassium, rubidium, cesium. Except hydrogen, these elements are highly metallic and are called alkali metals. Group 2 consists of beryllium, magnesium, calcium, strontium, and radium. These elements are metals but less metallic than group 1 elements. They are called alkaline earth metals. Group 7 elements consist of elements fluorine, chlorine, bromine, iodine. These are nonmetals and are called halogens. Group 8 elements or group 0 elements consists of helium, neon, argon, krypton, xenon, and radon. These are non-reactive elements known as noble elements, inert elements, or zero elements. Trends in the physical properties of elements in the periodic table. They include electronegativity, stroke, electropositivity, metallic character, 3 atomic radii, 4 ionization energy, 5 electron affinity, 6 melting point and boiling points. 1 electronegativity. In a covalent bond between unlike atoms, the shared pair of electron is not shared equally, because one atom with high attraction to electron will pull the shared pair of electron towards itself. The relative tendency of an atom to attract bonding electron is termed as electronegativity. The atom that attracts electron more strongly than the other is called electronegative atoms. These include oxygen, chlorine, nitrogen, chlorine, and so on. Electronegativity increases across the period from left to right because there is a progressive increase in the effective nuclear charge, or across the period both the nuclear charge and screening effect increase, but increase in the nuclear charge exceeds increase in the screening effect. Nuclear charge is the ability of the nucleus to attract the bonding electron, and screening effect is the repulsion of the outer electrons by the inner electron. So as we are going across the period, a proton is added to the nucleus, an extra electron is added to the outer shell. The force of attraction between the outer shell and the nucleus progressively increase, but also addition of an electron increases the repulsion of electrons on outermost shell, but the increase in the nuclear charge exceeds the screening effect, leading to increase in electronegativity. Electronegativity decreases down the group because down the group both the nuclear charge and the screening effect increase, but increase in the screening effect exceeds increase in the nuclear charge. The question may be, explain the variation of electronegativity of the following elements. 1. Carbon, germanium, tin. 2. Magnesium, aluminium, phosphorus, and chlorine. It is up to you to identify whether the elements are in a period or a group. In the first part, carbon, germanium, tin follows in group 4. You can say that from carbon to germanium to tin, electronegativity decreases, because from carbon to tin there is increase in nuclear charge and screening effect, but increase in screening effect exceeds increase in the nuclear charge. Part 2, magnesium, aluminium, phosphorus, and chlorine fall within period 3. We have already seen that across the period, electronegativity increases. You can say that from magnesium to aluminium to phosphorus to chlorine, electronegativity increases because from magnesium to aluminium to phosphorus to chlorine, both nuclear charge and screening effect increase, but increase in nuclear charge exceeds increase in the screening effect, leading to increase in electronegativity. Electropositivity, this is the relative ease by which an atom of an element loses valence electrons. When electronegativity is high, electropositivity is low. When electropositivity is high, electronegativity is low. So electropositivity and electronegativity vary inversely. When one increases, one decreases. Electropositivity also is the measure of the metallic character. The easier an atom loses the valence electrons, the more metallic it becomes. Electropositivity decreases across the period due to increase in the effective nuclear charge. We saw that across the period, both the nuclear charge and screening effect increase, but increase in the nuclear charge exceeds increase in the screening effect, which makes a progressive increase in effective nuclear charge. Electropositivity increases down the group due to decrease in effective nuclear charge, not nuclear charge. Previously, we have seen that down the group, both the screening effect and nuclear charge increase, but increase in the screening effect exceeds increase in the nuclear charge, leading to a decrease in effective nuclear charge. When electrons are weakly attracted to the nucleus, they will be easy to lose. So atoms with weak attraction to the valence electron will be highly electropositive. The question may be, describe and explain the variation of electropositivity in the following elements. It is very rare to ask you to describe the variation of electropositivity across the period and down the group. That will be very easy. But it is up to here to identify elements in a period and to identify elements in a group. You can say that in part 1, magnesium, calcium, sodium, and barium are in group 2 of the periodic table. So you can say that from magnesium to calcium to sodium to barium, electropositivity increases due to a decrease in effective nuclear charge. Beryllium, boron, carbon, and nitrogen are in period 2 of the periodic table. So you can now say that beryllium, from beryllium to boron to carbon to nitrogen, electropositivity decreases due to an increase in effective nuclear charge. Or we can say that from beryllium to boron to carbon to nitrogen, both nuclear charge and screening effect increase, but increase in the nuclear charge exceeds increase in the screening effect, leading to an increase in effective nuclear charge and a decrease in electropositivity.
It's now or never.
Metallic character. Since metallic character depends on how easily an element loses valence electron, metallic character varies like electropositivity. It decreases across the period due to increase in effective nuclear charge and increases down the group due to decrease in effective nuclear charge. Atomic radii is the distance from the center of the nucleus to the farthest electron under the influence of the nuclear charge of an atom. When electrons are strongly attracted to the nucleus, the atomic radius will be small because the outermost electron will be pulled to the nucleus. When electrons are poorly attracted to the nucleus, the atomic radius is going to be high. Therefore, across the period, atomic radii decrease due to increase in effective nuclear charge. Down the group, atomic radii increases due to decrease in effective nuclear charge and also addition of extra electron shells. Ionic radii. Cations have smaller radii than corresponding atoms because loss of electrons lead to an increase in effective nuclear charge on the remaining electrons. So the remaining electron will be strongly attracted to the nucleus and the size will decrease. So the more electron you lose, the smaller the cation becomes, because as you lose electrons, the nuclear charge on the remaining electrons increase and the size decrease. Anions have bigger radii than corresponding atoms due to increase in screening effect. The more electrons added, the bigger the anion becomes. A question can be, explain the following observation. 1. From sodium to chlorine along period 3 of the periodic table, there is a steady decrease in the size of the covalent radii. we have already seen that across the period, atomic radii decrease due to increase in effective nuclear charge. Both nuclear charge and screening effect increase from sodium, chlorine, but increase in the nuclear charge exceeds increase in the screening effect, leading to high attraction to the valence electrons. 2. Although potassium and required ions have the same number of electrons, the ionic radii of potassium ion is 0.132, while that of chlorine is 0.181 nanometers. We consider that the ionic radii of chloride ion is bigger than the ionic radii of potassium ion. The reason is that when potassium ion loses an electron, there is increase in effective nuclear charge on the remaining electrons. Electrons are going to be pulled closer to the nucleus. 2. Loss of an electron from potassium, there is a loss of a complete shell. But for chlorine, addition of an electron increases the screening effect on the added electron, which increases the ionic radii. Ionization energy, the minimum energy required to remove an electron from a gaseous atom or ion to form gaseous ion. The minimum energy required to remove an electron from a gaseous atom or ion to form gaseous ion. The ionization energy is thus classified as first, second, or third. When we remove an electron from an atom to form a positive ion with a single positive charge, first ionization energy. When we remove an electron from a gaseous ion with a single positive charge to form an ion with two positive charges, then to this second ionization energy. When we remove an electron from an ion with two positive charges to form an ion with three positive charges, then it is third ionization energy, and so on. So we should be able to distinguish between ionization energy and the first ionization energy. First ionization energy is the minimum energy required to remove an electron from a gaseous atom to form a gaseous ion with a single positive charge. Ionization energy is the minimum energy required to remove an electron from a gaseous atom or a gaseous ion to form gaseous ion. Variation of first ionization energy down the group. First ionization energy decreases down the group due to decrease in effective nuclear charge. Down the group, both screening effect and nuclear charge increase, but increase in screening effect exceeds increase in the nuclear charge. So the electron can easily be lost. Variation of first ionization energy across the period. Generally, first ionization energy increases across the period due to increase in the effective nuclear charge. However, it is not uniform, as seen by a plot of first ionization energy of period 2 element. From the graph, the first ionization energy generally increases across the period due to increase in effective nuclear charge. Then 2, the first ionization energy of beryllium is higher than that one of boron, because an electron from beryllium is removed from a stable full orbital, while that of boron is not. is removed from an orbital which is unstable, less than full orbital. The first ionization energy of nitrogen is higher than that one of oxygen, because from nitrogen an electron is removed from relatively stable half full orbital, while that of oxygen is removed from unstable more than half full but less than full orbit. The same reasoning can be extended to period 3. Generally, across period 3, the first ionization energy increase due to increase in effective nuclear charge. The first ionization energy of magnesium is higher than that one of aluminium, because from magnesium an electron is removed from a stable full 3s orbital. The first ionization energy of phosphorus is higher than that one of sulfur, because from phosphorus an electron is removed from relatively stable half full 3p orbital. Variation of successive ionization energy. Successive ionization energies increase due to increase in the nuclear charge as electrons are removed. When we remove an electron, the nuclear charge on the remaining electrons increase. But the increase is not uniform, because electrons reside in different energy shells. This is shown by a graph of successive ionization energy of sodium below. A graph of successive ionization energies of sodium. Ionization energy, number of electrons removed. Note that the general increase in ionization energy is due to increase in effective nuclear charge as electrons are removed. 2. The groups of electrons indicate the period of the element. Sodium is thus in period 3. The first group has 1 electron, the second group and the third group has got 2 electrons. This is the shell nearest to the nucleus, followed by this, followed by this. So this 1 electron is removed from the outermost shell because it requires the least amount of energy. 3. The number of electrons in outermost shell is the group of the element. Sodium is in group 1 because the outermost shell contains 1 electron. The big jump between the first and second electron indicates that the second electron is being removed from the inner full shell. From the graph of successive ionization energy of element X, we saw that it is in group 2 because it contains 2 electrons in outermost shell. It is in period 3 because it contains 3 groups of electrons, and that the element is magnesium because it contains 12 electrons. These are the number of electrons are equal to the number of protons. The number of protons identifies the element. Electron affinity. This is the energy involved in adding an electron to gaseous atom or an ion. When you add an electron to an atom, we have first ionization energy. When you add an electron to an ion with a negative charge and you get an ion with 2 negative charge, that's second ionization energy, and so on. We note that elements with high electronegativity, electron affinity is negative. Elements with low electronegativity have positive electron affinity. The electron affinity becomes more positive as electrons are added, because addition of electron will repel the next electrons coming. The first electron affinity of oxygen, for example, is exothermic, because oxygen has got high electronegativity. The second electron affinity is positive or endothermic, because the first electron repels the second electron. If we are to add another electron on oxygen ion, again the ionization energy is going to be more positive, because the two electrons already added will repel the coming electron. Melting points. These are temperatures at which solids are in equilibrium with liquids at constant pressures. Melting points are the measure of energy required to break down regular arrangements of atoms, ions, molecules in a solid state of a substance. The higher the temperature, the stronger the forces binding atoms, ions, molecules in the solid state. The melting points of elements in a period does not vary uniformly, because elements are bound by different forces as shown by the melting points of elements in period 3. A table of melting points of elements in period 3. From sodium to aluminium, the melting point increases due to increase in the strength of metallic bonds, which increases with the number of electrons contributed to form the metallic bond. Sodium has got 1 electron in outermost shell, so it contributes 1 electron to form metallic bonds. Magnesium contributes 2, aluminium contributes 3. The strength of metallic bonds depends on the number of electrons contributed to form the bonds. Aluminium, which contributes 3 electrons, will have stronger forces than sodium, which contributes 1 electron. From sodium to aluminium, melting points increase due to increase in strength of metallic bonds, which increase with the number of electrons contributed to form the metallic bond. The melting point of silicon is very high, because each silicon atom is bonded to 4 silicon atoms. By strong covalent bonds. The strong covalent bond require high temperature to break. That's why the melting point of silicon is very high. Phosphorus, sulfur, chlorine are bonded by weak van der Waals forces that increase with molecular masses. Phosphorus exists as P4, molecular mass 124. Sulfur exists as sulfur 8, molecular mass 256. Chlorine exists as chlorine 271. The sulfur with high molecular mass has high melting point compared to phosphorus, compared to chlorine with the lowest molecular masses. You can download the full notes of periodic table from Digital Teacher. You go to the website digitalteachers.co.ug, check under subject tutorials, then chemistry. When you click, you will download the notes of periodic table and other notes. Omutima kwe guteeterera, azalibwa bakungu, yakuzibwa bulungi atambula bulungi oba kiriba kitya ng'ono nsuula naye nga tulya naye oba muyaga gutya oba buzibu butya ono tufa naye ono yabasinga yono yeye omutima kwe guteeterera bulamu kwe butambulira oba butiti butya oba kwaka gutya ono ndifa naye era ndiba naye mubalungi gwe nnonze mubalungi gwe nfiira mubalagavu mulungi